Hello. Hello, everyone. Quick question. Did you find the link in the chat just now, or did you have the link before? Can you answer in the chat, please? Did you find the link to this webinar? I had the link, yes, because I've put it in the Google Classroom, right? So hopefully, yeah. So it's the same link every week. Took it from the archive classroom. Okay. Right. Just say, yeah, save the link. It's the same link every week. So we don't have to send it, and remember stuff like this. Okay. Who's had a look at physics? So how many problems have you managed to do for physics? Haven't NA if you haven't started. 5. Good. Managed to do 5. Any particular one that was problematic that you have like absolutely no idea how to begin? Maybe I can give you some hints. None. So Matti, is it question 6 that you had problems with, or 6 you have done? Problems with. Okay. I guess we can look at it. I'll just put that here. And yeah, I certainly will do some hints for that one, because that was the plan actually. So you kind of guessed what I wanted to do today. Okay, so I will share my screen. I hope it is recording. It is recording. Yeah, brilliant. Okay. And I need the chat, and I need the chat, and I need it on top. Always on top. Good. Okay. Perfect. You should be seeing my screen. If you're not seeing my screen, let me know. And the first thing I wanted to look at, it was initially in the problem sheet, but we've decided to take that away. Nevertheless, I would want to go through this because this will pop up in one of the next assignments. The discharge of a capacitor. You might have already done capacitors at school, and you might have done the discharge of the capacitor. And the discharge of the capacitor, you would see that the Q is equal to Q0 E minus T over RC. So who is familiar with this equation? 1 or 0? Who's familiar? 1, 0 for not familiar. Okay, most people are familiar with this. Okay, so this is the equation for the discharge of the capacitor. This is A-level stuff. This is A-level. If you haven't done it at school, you will do it very, very soon. Adam. Right. Okay, so we have a capacitor that is charged with a capacitance C, and we have a resistor R. Another question. Do you know how to derive this formula? 1 or 0, please. If you know how to derive this formula, type a 1. If you don't know how to derive this formula, put a 0. Okay, Kieran, good, but it seems like you're the only one today. So I will go through that. Let's say you have a charged capacitor. You have a charged capacitor, and it is discharge. Oh, what am I doing? We charged capacitor, positive and negative, and usually we draw something like a switch. When the switch is closed, current starts to flow. Current starts to flow in this direction from plus to minus, from high potential to low potential, and the capacitor starts to discharge. Now, the charge on the capacitor, the first thing that we know, the charge on the capacitor is C times V, times the voltage on the capacitor. Now, we also know that the current is equal to voltage divided by resistance. That's the Ohm's law. Okay. And we also know that the current is the rate of flow of charge. It's the charge over time. The only thing is, I have to mention, because a current leads to the discharge of the capacitor, so it's the change of the charge. So dq is the change of charge, similar to delta q, right? Delta q and dq are very similar. It's just dq is a much smaller change of charge. So this has to be negative. Negative because it is discharging. Negative because discharging. Charging. All right, so now we can set up a differential equation. So we have Kirchhoff's second law. Kirchhoff's second law says that the sum of voltages, well, voltages in parallel are the same. Basically, Kirchhoff's second law says that voltage on the capacitor is equal to voltage on the resistor, right? So there's nothing serious here. And the voltage on the capacitor is Q over C. Q over C. And voltage on the resistor is IR. IR. But we've already established that I is dq. So Q over C is equal to R minus R dq over dt. Okay, everyone on board so far? So all I have written here is that voltage in parallel is the same. So this is nothing else than saying voltage in parallel is the same, right? From 0 to 10, please, in the chat. Are you on board with everything so far? Henry, oh, that's a 10. Okay. Okay, good. And then this is the differential equation. How do I know that it's a differential equation? Well, it contains Q and it contains dq dt. Right? That's how I know it's a differential equation, because it contains the function and the derivative of that function. So this is a differential equation. Now I separate the variables, separate variables. There are two variables, Q and T, because R does not change, C does not change. Separate Q and T. So I have dt over C. Oh, I can just dt is equal to, I'd say minus dt is equal to RC dq over Q. That's what I did. Everything that contains T is now on the left, and everything that contains Q is now on the right. And this calls for integration. We integrate both sides. integrate. So the integral of dt, minus stays where it is equal to RC integral of dq over q. What's the integral of dt? Somebody? Differential equation. Differential equation contains it is minus t indeed. Well, technically it's minus t plus c. So from here I have minus t. Now, okay, I'll write plus c1 just to make it clear what I'm doing next. Equals what's the integral of dq over q? Ln q, by all means. It's a ln q ln q plus, well, plus c plus c2. There is a problem. We can't use c because we already have c. So let it be k, k1 and k2. Now, RC ln q plus k2. Now, this is the first method. This is the method I don't really like. First method. Because you end up with k's. But we can put k2 to the left-hand side, minus t plus k1 minus k2 equals RC ln q. And k1 minus k2, let it be just k, right? Because these are arbitrary constants. K2 equals k. So minus t plus k equals RC ln q. We rearrange that. Minus t plus k over RC equals ln q. We found e to the power minus t plus k over RC equals q. And what is k? Well, we can write this as e to the power minus t over RC multiplied by e to the power minus k over RC. And because this is a constant, we can just name it, like, let's say b. Q equals b multiplied by e minus t over RC. So what is b? What is b? Well, to find b, we substitute. So we know that when t is 0, q is q0. It's the initial charge. Yeah, so initially, the charge on the capacitor is plus q0 and minus q0. Is the initial charge. And we can write it like this. Q is q0. So q0 is equal to b multiplied by e to the power 0. Oh, so b is q0. So we can write this down. Yes. Oh. B is q0. Therefore, the q is equal to q e minus t over RC. And this is the derivation of the formula. Now this is the first method using k. Yeah, using a constant, integration constant. I don't particularly like this method because it becomes very messy right about here. I say this is messy. Like renaming this as B and then trying to figure out what B is. It's very easy to get lost on along the way. What I do instead, I say, well, the second method, I have this differential equation. Well, it's the integrated version, dt equals RC, integral of dq, q. I say, look, q changes from q0 to q to q, or q final. But I mean, we call q final is q. Q changes from q0 to q. Time changes from 0 to t. Okay. So time changes from 0 to t, and q changes from q0 to q. And now we integrate, but now we integrate it with limits. And look what happens. The integral of this is t minus t between limits 0 and t. Then we have RC, and then we have logarithm of q between limits q0 and q. So we have minus t equals RC ln q minus ln q0 minus t over RC is equal to ln q over q0 q over q0 is equal to minus t over e to the power minus t over RC. Q is equal to q0 e minus t over RC. This is it. So this is I think this is a much more elegant solution to the differential equation. Okay. And now I've advertised the second method. Which method do you prefer, 1 or 2? Which one do you prefer, 1 or 2? Yeah, you just need to very carefully analyze it because you are allowed to put the limits. You're allowed to put the limits when you're doing a differential equation. And so let's go through problem 2. Emptying a swimming pool. So imagine a swimming pool, like a normal swimming pool which you go to in the community center or whatever, wherever. And imagine it had a hole in the bottom, just like your bathtub. So a bathtub is typically a pipe of 1.5 inches. So let's find the area. So we have a bathtub, not a bathtub, a swimming pool. And there's a pipe at the bottom. And the cross-sectional area, yeah, let's go with small a. Area is pi r squared. Well, so 1.5 inches, that's 1.5 times 2.54. That's 3.81 centimeters divided by 100. So 0.0381. So pi multiplied by answer squared. That is roughly 5. It's pi Oh, pi d squared over 4 over 4. 1 times 10 to the minus 3. 0.001 square meter. Okay, that's this area. So if it's 1.5 inches, it's about a 1,000th of a square meter. 1.5 inches. Okay. That's the cross-sectional area of the pipe. That's a normal. That's your normal bathtub drain. Okay. And let's see how long it will take for a normal swimming pool to empty through that. Okay. So this is 1.8 meters. And this is the cross-sectional area. Okay. So what we have is a jet of water. A jet of water traveling at speed v. Traveling at speed v. And we know by Torricelli's law, v is equal to square root of 2gh. 2gh. And that's quite interesting because h is the depth of the swimming pool. H is the depth of the swimming pool. And if you write down mgh is equal to 1/2 mv squared, m cancels and you have v equals 2gh, v squared. So v equals square root of 2gh. So it's exactly what you would have if water was falling from the top. If water was was falling from the top like this, for example, yeah, like this, the speed at the bottom would be exactly the same, 2gh. Well, I mean, it's not a coincidence, but it's an interesting thing. Like water leaking from the bottom of a tank has the same speed as if it was falling from the top of the tank. Right. And if you imagine this is a cylinder, this is like a cylinder of water. And in time t, in time dt, it travels v dt, a distance of v dt meters. So the length of this is v dt. Okay, travels v dt. So the volume is equal to v dt multiplied by A, which is the cross-sectional area. Volume per volume in time. Well, it's the volume. dV. So dV volume is equal to VA dt, and we know V, which is equal to A square root of 2gh dt. Okay. And now we need to express the volume in terms of, well, we divide by dt. Divided by dt, dv dt is equal to A square root of 2gh. That's the rate at which the volume is decreasing. So technically it's going to be minus. It's because it's a change of volume is minus this. Minus because the volume is decreasing. So rate of change of volume. Rate of change of volume. All right, now the volume of the tank. The volume of the tank is length times width times height. So length times width, that's 25 times 10, so 250 times h. Now we can differentiate that. dv dt is equal to 250 dh dt. And we can plug that in. So the equation that we had was dv dt is equal to minus a square root of 2gh. And now this is 250 dh dt equals minus a square root of 2gh. And look at that. You can separate the variables. Separate variables. So this is your differential equation. This is the differential equation because it contains h and it contains dh over dt variables. So 250 dh over square root of h equals minus a square root of 2g dt. And now we integrate. Now this is a constant, so this can be outside the integration. Time changes from 0 to t, and height changes from 1.8 meters to 0. We're emptying the pool. Now we just integrate. So this is going to be 250. This is h to the power minus a half. So h to the power a half divided by a half between limits 1.8 and 0 equals minus a square root of 2g. These are constants. And then t between limits 0 and t. So 250 multiplied by minus 1.8 to the power 1/2 divided by a half minus a, which is minus 0.001 square root of 20, because 2g is 20, multiplied by t. And you can easily work out t from here. So 250 times 1.8 square root of 1.8 multiplied by 2 multiplied by 2 divided by 0.001 divided by square root of 20. 150,000 seconds, 50,000 seconds, which is approximately 42 hours. 42 hours. Now, it seems like a long time. Sorry. But when I was, I think 17 or 18, I had a small job on the side, and I was asked to empty a swimming pool using an electric pump. So I put the electric pump, and I knew that it pumped quite a lot of water. So I knew I could fill in a bathtub in less than like 10 minutes or something. And I was trying to empty a swimming pool. It took me about 3 days, and it was a small swimming pool. Apparently, there's a lot of water in the swimming pool. Any questions here? How well did you understand the solution, guys? From 0 to 10, please. Okay, very good. Now, terminal velocity. Terminal velocity, so imagine you are, a person is falling through the air. And so what are the forces acting? So we have gravity, mg. We have, well, no, we have the air resistance. Air. The air resistance at small speeds can be modeled. So F air is equal to K multiplied by V for small speeds, or it's equal to, like a different, let's call it not K, but alpha V for small speeds, or beta V squared for higher speeds. That's small speed and high speed. So for a skydiver, that would definitely be beta V squared. But for something slow, it's going to be less. So let's do the skydiver with high speed. I think that's the additional problem. That's the final problem, and it's quite messy in a way, but let's see. So first of all, you write Newton's second law. Newton 2. Mass acceleration is equal to the resultant force, and the resultant force is mg minus F of air. In other words, ma is equal to mg minus beta v squared. And that's your differential equation. Why is it differential equation? Because A is dv over dt. M dv dt is equal to mg minus beta v squared. That's a differential equation. Because it contains v and it contains dv over dt. Now, the tricky part here is the separation of variables, because it seems like it's impossible to divide to make it that v is on one side and t is on the other side, because there's this term here. Because I mean, if it was m dv over dt equals minus bv squared, that would be super easy. You would just do m dv over v squared is equal to minus beta dt, right? That's separation of variables. Who can help me how to separate this? How to separate the variables here? Jeez. Use your microphone, just shout out. How do I separate variables here? I remind, the variables are v and t. V and t are my variables. Come on, any ideas? Any idea? Welcome. Very good. You want to divide both sides. Can't divide. Yes, Maya, well done. You divide both sides by mg minus beta v squared. M dv over mg minus beta v squared is equal to dt, because there's nothing left here. Right. And now I see everything, if v is on the left and t is on the right. Okay. Now, before integrating this, because this does not look like something I want to integrate, I'm gonna cancel. What can I cancel here? I'm gonna take minus b. I'm gonna take minus b as a common factor on the bottom. So it's going to be m dv mg over beta minus mg over beta minus v squared equals dt plus v squared, and then minus 1 over beta. Okay, I'll give you some time to absorb this. So I've taken beta out of the brackets on the bottom, and I'm left with this. So why did I do this? Because now I can write, well, I can get rid, I can take beta to the other side. So m dv over v squared minus mg over beta. And mg over beta equals minus beta dt. And this doesn't look pretty, but actually it's solvable. It's solvable if I am able to do this integral. Now this integral is not particularly easy. So the integral is v changes from 0 to v terminal. And t changes from 0 to. Okay, no, we don't do v terminal. Sorry. V changes from 0 to v, and t changes from 0 to t. And then you differentiate. And to differentiate this, you need the integral of 1 over not this one, minus a squared. Not this one, this one. So here it is. I'm going to use this integral. Okay, so we have m 1 over 2a, and a is in this case is square root of mg over beta, square root of mg over beta, ln v minus square root of that, v plus square root of that, between limits 0 and v is equal to minus beta t. And all you need to do is just to simplify this. Simplify. I'll leave you to do the fun stuff. Simplify. And this is problem. This is the final problem. This is the problem 14. Okay. But then there's another question. what is the terminal velocity? Can we work out the terminal velocity without solving this differential equation? Because you will see that this differential equation it has a solution, and it's something in the lines of V is equal to V terminal minus V terminal E minus KT. The solution will be in this form. And as t increases, this becomes 0. As when t tends to infinity, this tends to 0. And V becomes V terminal. V tends to V terminal. Please do figure that out. So from here, simplify, find V. Find V from this equation. I'll leave you to it. But can we figure out the equation, the terminal velocity, without referring to this stuff? Well, as a matter of fact, we can. Because what happens at terminal velocity? Where can we write? I can write here. At terminal velocity. At terminal velocity. dv over dt is equal to 0. The change of, yes, dv dt is equal to 0. And here, so we have mg is equal to beta v squared. So v is equal to mg over beta. And if you know the values for mg and beta, then you're good to go. Or you can work out the value of beta from the terminal velocity. So for example, we have m equals 70, and the velocity is 70. So we have 70 equals square root of 70 times 10. Yeah, don't feel that you have to put 9.8 every time. Not, at least not for COMPOS. Beta is beta. So you can work out beta equal to square root of 7, which is approximately 2. I forgot the square root of 7. Shame on me. 2.65. 2.65. All right. Hope that makes sense. Now let's do some rocket science. I was very pleased with the title. I don't know. I hope you were as excited as I am. When people say it's not rocket science, thinking that rocket science is something particularly difficult. Well, not really. Like, rocket science is mostly just the one equation. Of course, not considering the flow of rocket fuel and not considering rocket engines. If you forget about how the rocket engine works, everything else is simple. Okay, Michelski and Tsiolkovsky equations. So basically we used the conservation of momentum here. So we have a rocket of mass m. It burnt off some fuel of mass dm, and the mass of the rocket became m minus dm. As a result, the rocket has increased its speed by delta v, by dv, and the gas went the other way. Now we use conservation of momentum here, where F is an external force on the system. Now, one thing I'm using here is I'm saying, look, dm is very small. dm is small. dv is small. But dm dv is small on another level. It's small compared even to dm, right? We say it's a different order of different order of magnitude smaller, right? So if dm is 10 to the minus 3, dm dv is 10 to the minus 6. So it's 1,000 times, well, it's infinitely smaller than the infinitely small. Therefore, even small. That's why we can set it to 0. Okay. Right. It's next order of magnitude smaller. So we can rearrange this, and we have this differential equation, which is quite cool, actually. And the question is, how much fuel? Oh, this is called the Michersky equation, by the way. Michersky equation. So what the question is, how much fuel must a rocket burn per second to hover stationary? Okay. Well, to hover stationary, that means that dv over dt must equal to 0. Okay, so we have m dv over dt is equal to u dm dt plus F, external force. And the external force in this case is gravity, and gravity is down. Okay, so we have this is equal to 0, equal to U dm dt minus mass mg, mass of the rocket, times g. So dm dt is equal to mg over u. A very simple one. And this is the rate of change of mass, right? So it's a rate of change of mass. So that is the amount of fuel per second, rate of burn of fuel, rate of burn of fuel. And then you just plug things in. Now your problem is slightly harder. I think it's problem 5, where you need to give your answer as a function of time. So I'll leave you to work it out, because dm dt, m changes. Yeah. Rate of burn of fuel. But this is a function of time. That's important. Yeah, so in this case, mg 3 tons, 3,000 times g 30,000 divided by 3,000, 10 kilograms. That would be 10 kilograms per second. But if you were talking about this, because as the rocket burns fuel, as the rocket burns fuel, it loses mass. Okay, so you need to take that into account, and you need your answer in terms. Now, this one, solve example 3. Assuming the rocket is flying vertically upwards in the gravitational field of the Earth. Ignore air resistance and the change of gravitational field with height. Assume that mass mu of the fuel burned per second to be constant, and that all fuel is used up in 1,000 seconds. So you have a rocket, and there's the force, the thrust, and there's the external force, external force is mg. So you write the same equation, m dv dt equals u dm dt. So now I'm doing minus mg. I'm doing this. I'm doing this problem. Right. I multiply everything by dt. Multiply everything by dt. M dv equals u dm minus mg dt. And now, like, I'm using a trick. I'm using like a super duper trick. I'm just integrating this, and integrating this. Now I'm integrating this. V changes from 0 to V final. I'm integrating this from M initial to M final. And I'm integrating this from 0 to T. And now I'm left with something. MV final is equal to, oh, sorry, of course, I can't do that. Very sorry for that. I have to divide by M as well. I have to divide by M as well. So that's dm over m. Vf is equal to u logarithm of mf over mi minus gt. So Vf plus gt is equal to u ln mf mi. And what do we need to find? Oh, we need to find how much fuel. Okay, so we have e to the power Vf plus gt over u equals m final mi. And you can work it out from here. But there's also a limitation, something about the fuel being used in the first second, and things like that. Right. Moving on. Problem 5, the problem of the damped oscillator. Now, this is an excellent one, excellent problem. Now we have an oscillator. Well, it's oscillator with friction, but it's not exactly friction. It's resistance proportional to the speed of the oscillator. So we have K, that's the spring constant. We have the oscillator, but going left and right. So what are the forces? So let's say this is the neutral position. We move the oscillator to the right. And let's say, and what are the forces acting on it? Well, if it's here, mass acceleration, we have the kx is equal to minus kx. That's the Hooke's force, the Hooke's law force. But also, there is the resistance. So it is the let's use the same notation. B, okay, minus B multiplied by V, where B is the coefficient of drag coefficient. So drag is equal to minus BV. Okay. And we can rewrite this mx double dot, because acceleration is the second derivative of x, equals minus kx minus bx dot. And if we write this mx double dot plus k plus bx dot plus kx is equal to 0, this is a homogeneous differential equation of the second order. It's a homogeneous differential equation. Of order 2. Have you done differential equations at school? Differential equations of order 2 at school? Anyone? 1 or 0? Of order 2, Adam. Yeah? Okay. Yeah, so you could it looks like this: a y dash dash plus b y dash plus c y is equal to 0. That's how it looks like in everyday life. In maths, that's how it looks like in maths. And in our case, it's just mx double dot plus bx dot plus kx equals 0. And we divide by m. We have x double dot plus b over m x dot plus k over m x equals 0. And if you remember, omega squared is k over m. So we replace that with omega. So x double dot plus, and b over m, we just use a gamma. B over m is gamma. Gamma x dot. B over m is gamma. Plus omega squared 0. That's the natural frequency. That's the frequency of the oscillator. Equals 0. This is a differential equation. And we have the characteristic equation. Which is no, sorry. The solution is x of t. Solution x of t is equal to a multiplied by e alpha t. How do we prove that? Well, let's find prove that it is a solution. What you do is you find x dot is a alpha e alpha t, and x double dot is a alpha squared e alpha t. So you plug that in. A alpha squared e alpha t plus gamma a alpha e alpha t plus omega 0 squared a alpha AE alpha t equals 0. We cross out AE alpha t. Alpha squared is plus gamma alpha plus omega 0 squared is 0, which is a quadratic equation in terms of alpha. Yes, it's a quadratic equation in terms of alpha, and therefore alpha is equal to plus or minus, minus gamma over 2 plus minus square root gamma squared over 4 minus omega 0 squared. Now, the solution is alpha is real if gamma over 2 is greater than omega 0. Alpha is complex, well, greater or equal, complex if gamma over 2 is less than omega 0. Okay. And this determines what kind of damping you have. If it's a real solution, that means there will not be any for a real solution, there will not be any repeated motion. Okay. So what does it mean? So if the solution is if alpha is real, you displace a pendulum. So you have a pendulum, you displace a pendulum, and you release it. It just slowly goes back to the original position and stops. Because the damping is so large, that it goes, you release it and it just goes and stops. This is what happens when alpha is real. There's no repeated motion. If alpha is real, no repeated motion. That's no repeated motion. We call it over damping or critical damping. Over damping if when gamma over 2 is greater than omega 0. Well, actually, it's gamma greater than omega 0, and critical damping, when gamma is equal to omega 0. Okay. So in school, you just know what they just explain to you what is overdamping. Overdamping is no repeated motion, and here we actually show you the maths. I try at least to show you the maths how you do it. So overdamping is when gamma is greater than 2 omega 0. Gamma is the coefficient of damping and of a system, and when gamma is equal to, it's critical, no repeated motion. So you can imagine a pendulum in a can of oil. Yeah, you release it and it just goes slowly back. If it's underdamping, that means gamma is less than 2 omega 0. And the solution is complex. And you have the graphs. You have the graphs here. So you displace the pendulum from some position, initial position, and if it's underdamped, it goes like this and slowly dies out. If it's critical damping, it goes like this. It quickly goes back to the original position. And if it's overdamped, it just takes more time. Okay. Make sense? Make sense? How well do you understand what's happening here? Now, if the solution is complex, thank you for letting me know. If the solution is complex, then alpha, if gamma is less than 2 omega 0, then alpha can be written as minus gamma over 2 plus or minus I omega 0 squared minus gamma squared over 4. So we take the I out of the square root. This becomes positive. And then the solution can be written as xt is equal to E minus gamma t over 2. Oh, did I miss something? Oh, no. Gamma t over 2. A plus E I square root of omega 0 squared minus gamma squared over 4 t plus a minus E minus 1 minus I omega 0 squared minus gamma squared over 4 t. And A, where A plus and A minus are just some constants, which are determined by the initial positions, determined by initial position of pendulum. So it's not that important what A plus and A minus are. So for example, well, yeah. And this can be rewritten. This is equivalent to x of t is equal to E minus gamma t over 2 c multiplied by cos square root of omega 0 squared minus gamma squared over 4 t plus s multiplied by sine square root of omega 0 squared minus gamma squared over 4 t. Now it looks horrible. It's actually not. C and S, again, C and S are constants. Determined by initial conditions. Example: if a pendulum is drawn back, is released from maximum position, then C is 1, S is 0, and the equation becomes x of t equals E minus gamma t over 2, C multiplied by cos omega 0 squared minus gamma squared over 4 t right? And this thing, omega 0 minus gamma squared over 4, square root of that, it's the frequency of damped, well, angular frequency, of course, angular frequency of damped oscillations. If damping is small, that means gamma is approximately 0. That means omega 0 squared minus gamma squared over 4 is approximately omega 0. You see what it is? This is the frequency of damped oscillation, so we can call it omega star. When you introduce damping into the system, the pendulum goes slower, and that makes perfect sense. Okay. Frequency decreases. It becomes omega minus something. Okay. How the first equation more. Sorry, which one? Jasmine. Jasmine is asking, could you explain how you got the first equation more? Which one? Sorry. Okay. Yes, that is a good point. Thank you. Well, we know that the solution x of t is equal to an arbitrary constant a plus that's multiplied by e to the power alpha 1 t plus a minus multiplied by e alpha 2 t. That's the general form. That's the general form of the solution. Yeah, Jasmine, have you met this before? I never met that. Okay, if you have an equation y double strife a plus b y strife plus c equal 0, that's a differential equation of second order. You have the characteristic equation lambda squared a lambda squared plus b lambda plus c equals 0. That's a quadratic equation, and lambda 1 and lambda 2 are the solutions. That means y is equal to an arbitrary constant a multiplied by e to the power lambda 1t plus b multiplied by e lambda 2t. Well, lambda 1 and lambda 2 are the solutions of this equation. This is something you will prove when you do second order differential equations. So this is second derivative of y plus first derivative of y plus c. You get a characteristic equation, which is a quadratic equation. You solve it and you write down the solution like this. Well, let's look at an example. Let's say you have y double strife minus 5y strife plus 4y is equal to 0. The corresponding characteristic equation is lambda squared minus 5 lambda plus 4 equals 0. So lambda 1 is equal to 1, lambda 2 is equal to 4. These are the solutions of the quadratic equation. And that means y is equal to a multiplied by e to the power x plus b multiplied by e to the power 4x, where a and b are determined by the initial conditions. A and b are constants determined by initial conditions. Now let's prove that this is a solution. Is this actually a solution? Is this a solution? Question mark. Well, let's see. We find the derivative. It's equal to a ex plus 4b e 4x. Y double strife is a ex plus 16b e 4x. We plug that in. Plug in to the original equation. Yeah. So we have a ex plus 16b e 4x minus 5 multiplied by a ex plus 4b e 4x plus 4 a ex plus b e 4x equals 0. And we can see that a ex minus 5a ex plus 4a ex is 0. 16be 4x minus 20be 4x plus 4be 4x is 0 equals 0. So true. So this is a differential equation. This is a differential equation, and this is the solution of that differential equation. Now, we have, this is the differential equation in our case. This is the differential equation. And this is the solution. You can prove that it is the solution. Well, I mean, this is the solution. This is the solution of that equation, okay? This is the solution of that equation where a plus and a minus is just arbitrary constant. Now, alpha 1 is minus gamma over 2. It's just the solution of this quadratic equation. This quadratic minus gamma over 2 plus I square root omega 0 squared gamma squared over 4 over 4. And alpha 2 is minus gamma over 2 minus I square root of omega 0 squared minus gamma squared over 4. And all we need we plug that into here. All we do is we plug that into here. So we have xt is equal to a plus multiplied by e to the power minus gamma over 2t plus I square root of omega 0 squared minus gamma squared over 4t plus the same thing but with a minus and as you can see we can x of t is equal to, they have a common factor here. It's e minus gamma over 2t multiplied by, open bracket, a plus e I square root of omega 0 squared minus gamma squared over 4t plus a minus e I square root of omega 0 squared minus gamma squared over 4t. Okay, that's that. Does that make more sense? That's a question for everyone. Does this make more sense now? Okay. I mean, it's not the easiest thing in the world, but this is the solution of the differential equation, and you will need to prove the equivalence of these two solutions. One of the tasks, you need to prove that these are equivalent. Well, to do this, you need to use this formula. You need EI theta is equal to cos theta plus I sine theta. Or in other words, E I square root of omega 0 squared minus gamma squared over 4t, is equal to cos of that thing plus I sine of that thing. And it works out beautifully. You will, once you do this, yeah, I hope you will be just thoroughly enjoying this process. Okay. Now this term, as I said, this because if you look at the equation of simple harmonic motion, you have amplitude multiplied by cos omega t. Here, it's the same thing. It's the same thing. The amplitude, this is the amplitude. And this is the frequency. This is the frequency. This is the frequency. This is omega. And this is the amplitude A. It's just in simple harmonic motion, amplitude is constant. And in damp oscillation, the amplitude decreases with time. So the amplitude is equal to C multiplied by E minus gamma T over 2. This simply means that decreases with time. Decreases with time. And your omega star is square root of omega 0 squared minus gamma squared over 4. The frequency is lower than simple harmonic motion, lower because there's friction. Lower than SHM because of friction. And if gamma over 4, if gamma over 2 is greater than omega, then it's going to be a square root of a negative number. That simply means there's no frequency. Yes, the frequency does not exist because there's no time for repeated motion. There's no repeated motion. Comparing to SHM. Okay. Let's look at the forced oscillations as well. This is a very important piece of physics. The solution for a forced oscillator. So for the forced oscillator, for the damped oscillator, the equation was x double dot plus gamma x dot plus omega 0 squared x squared x equals 0. Now it's this. So the difference is that here we have a 0 on the right, so that's a homogeneous, and this is a non-homogeneous, this equation. Now without the solution of this is quite complex. It's quite, well, it's literally complex because it involves complex numbers. There is a video of the solution, but this is the solution. This is x. You can prove that it is a solution by direct substitution. So you substitute that in and you confirm that it is in fact the solution. And I think this is one of the tasks. Yes, it is. It is one of the tasks. So I won't do this. So to do this, so that's problem 10. You just need to find x dot, the derivative, and x double dot, and sub that in, So that's problem 10. Find and sub. But this is the solution. Let's analyze the solution. What is the solution telling us? So x of t is equal to f0 divided by m square root of omega 0 squared minus omega squared 2 plus omega gamma squared multiplied by cos omega t minus phi. Doesn't it look familiar? Doesn't it compare to x of t is equal to amplitude multiplied by cos omega t plus phi? This is simple harmonic motion. So what this huge thing represents the amplitude. That's simply the amplitude. Amplitude of forced oscillations. Okay, let's play around with it. Desmos. Y is equal to and it's a function, and importantly, it's a function of omega. Yeah, the amplitude is a function of omega because omega 0 is the natural frequency. Gamma is the coefficient of friction, or coefficient of drag. M is the mass. So and F0 is the amplitude of the external force. So we have the external force F divided by M square root open bracket square root open bracket omega. No, it doesn't like omega. Okay, let's call it A. No, A is a bad one. B squared minus x squared plus gamma, let's call it G, x squared. And now add all the sliders. And limited, because amplitude cannot be negative, x is greater than 0. All right, so F is the external force, is the amplitude of the external force. And if I increase that, well, the amplitude increases. Yes, this is the graph of amplitude versus omega. Omega is the frequency of driven oscillations. So that's how it would happen if I change the force. If I change the mass of the oscillator, we have a similar thing. Of course, you reduce the mass, the amplitude increases. You increase the mass, the amplitude decreases. So there's nothing new here. I mean, it's quite predictable what happens when I change the mass. Now, B is the natural frequency. Is the natural frequency. So let's make it bigger. Let's make it 3 radians per second. And now G, finally, is the most interesting one. G is the coefficient of drag. Look what happens when I, well, no. Okay, drag from 0 to 5 with a step of 0.1. Look what happens when I increase the drag. Look what happens when I decrease the drag. You've probably seen this picture. You've seen this picture. This is the amplitude of driven oscillations. And we can see that when the amplitude gets close to the natural frequency, of the oscillator, then the amplitude increases greatly. This is resonance. This is the resonance curve. This is the resonance curve. Let's see what it does. Resonance curve. This is the omega 0. This is the natural frequency. This is the amplitude. And this is the omega. This is the driver frequency. Driver frequency. Have you done resonance in school? Yes or no? Have you done resonance in school? So you've seen this curve. And this is the equation of that curve. Here it is. It's just a solution of the differential equation. And you can see that when the driver frequency gets close to the natural frequency, the amplitude increases greatly. And at some point, if the friction is, if it's an undamped oscillation, it just goes to infinity. It goes to infinity. And this is very this is easy to explain, because that means that this thing is 0 and this is 0, so it's division by 0. Yes, if you have no, if there's no friction, this term is 0, and this is also 0, so we have infinity. We have an oscillations that grow infinitely. And if you increase the friction, the resonance curve becomes wider and less pronounced. So at some point it's just nothing. Okay. If you want to play around with this curve, here you go. Okay. GXM. GX. G represents the gamma, the coefficient of drag. G is the coefficient of drag. B is the natural frequency. M is the mass. F is the amplitude of the external force. Okay. And well, there are fantastic examples of resonance. You've probably seen some of them. So flutter, airplane, flutter. So flutter is when the wing of an airplane, if you bend it and let go, it will go like this, bouncy, 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 bouncy. Okay. Now the wind, when you are passing through turbulent air, the vortices, they hit the wing, and if the frequency at which the vortices hit the wing matches the natural frequency, the wing starts swaying. Look what happens. You see the wing, the tail starts to sway. This is another example, the Tacoma Narrows Bridge. If you ever noticed, when you're standing on a bridge and a heavy truck is passing, the bridge starts to sway. The same happens with the wind. When the wind vortices hit the bridge at the exact precise moments, you have resonance. So the natural frequency of the frequency of the wind matches the frequency of the vortices, matches the natural frequency of the bridge. You have this swaying of the bridge. Now this is real time, real footage. This is a video from the Tacoma Narrows Bridge collapse in 1947, I believe. You've probably seen it at school. Right. So you can watch that later if you wish. Is it just the one example? No more examples? Okay. Right. Just one example. I was hoping for a bit more, for more examples. Ah, this is Flutter. Yes, of course. Oh, it's the same. Oh, here. Yeah, you can see a glider fluttering. So this usually happens when you increase the speed. So if this happens to an aircraft, you just need to slow down, and the swaying should stop if you can do it quickly enough. So these are examples of flutter. Okay. This, yeah, you can see the tail vibrating. Now, I don't know what this is, but this shouldn't be fluttering. Like passenger jets should not be put into the position of flutter. Okay, they always do a flutter test. So, for example, the A380, the super jumbo jet, it went through a flutter test. So they actually pointed the airplane down and it started shaking, but not in a normal flight. It should never do that in a normal flight. So here you can see the tail shaking, so flutter. This often, well, at least it used to often lead to disaster. So the planes would just break into pieces. Now they go through much more rigorous testing, and they don't do that. Ah, here it is. This is a model aircraft. So it's, you can see it just falls out of the sky because of flutter. Yeah, and here's the aerodynamic tube tests you can see. So these are examples of resonance. And yeah, okay, well, I'll leave you here. Hope you found this useful. Not too I hope you are not too overwhelmed by the maths, by the amount of maths. Yes. So enjoy the assignment. All right. See you, everyone.
I was just going to quickly ask, if alpha is real, does that mean there's no repeated motion?
Yes, there's no repeated motion.
Okay. Thank you.
So so as I said, imagine a pendulum in oil. Yeah, you have a big tub of oil and you have a pendulum inside. You let go, it just slowly goes back to the neutral position and stops. Does that make sense?
Yeah, so then alpha would be real in that case.
Yes, alpha would be real.
Okay. Cheers.
Oh, Judah. Okay, let me have a look. Have I? Okay. I'm surprised that we have still people who don't know. Give me a moment. Could you send me a private message with your name, please? Judah? Oh, you're not.
Hello? Huh?
Hello.
Is he on Telegram?
Sorry.
You said I should send you a private message with my name.
Yeah, on here.
Oh yeah.
Yeah, in Zoom.